So now we come to primary treatment. So we have a wastewater treatment process. First step, preliminary treatment. All treatment facilities have some form of preliminary treatment, either bar screen, or at least bar screens and grit removal, sometimes equalization. Then we get to primary treatment. So another name for primary treatment is settling. These are essentially synonymous. When you hear primary treatment, you should think these are tanks essentially designed to have the water slow down so that particles and solids can settle out of the waste stream and can be removed. So we call these things settling basins or clarifiers. A clarifier clarifies the water by separating out the solids. So here's a couple examples of circular clarifiers, which are the most common design. And the way these tend to work nowadays is the wastewater comes through in this. It comes into the tank in the center of the tank. Usually a pipe comes up from the bottom, and the wastewater enters near the top or somewhere in the center, usually near the top, and then flows outwards toward the edges. And along the edge on the top is an overflow weir that the water can go over and into a little channel that's on the outside, where it then gets collected and moved on to the next process. So that way, as the water comes in the center and moves towards the outside, the solids have a chance to settle towards the bottom of the tank while the water gets pushed over these overflow weirs. And then these two bars right here are constantly rotating around, essentially scraping solids off the bottom of the basin and into a collection area, usually at the center of the tank. So the tank is usually shaped something like this on the bottom so that the solids can kind of be collected. Typically have a detention time of about 2 hours or more in order to achieve adequate settling. And if you have a detention time of that, we're typically going to remove about 60% of the total suspended solids coming into the plant and about 30% of the influent BOD. So that's quite a bit for just one process that doesn't really require much technology or any kind of biological treatment. We're removing a significant percentage of what's coming in that are, again, our goal of wastewater treatment, our primary goal is to take out TSS and BOD. Additionally, hopefully nutrients, inactivate pathogens, maybe remove some toxins like metals. But this is a primary goal, and primary treatment is going to take out quite a bit of that. So what's going on here? The theoretical background, there's a couple kinds of settling theories, Stokes settling, and then what's the other one? Newton's law. So Stokes' law and Newton's law are two possible ways to calculate what's going on. In Stokes settling, we're assuming laminar flow, so very slow settling, which is a pretty good assumption for wastewater treatment. In water treatment facilities, we typically might have more turbulent flow going on in our settling basins, but in wastewater, we tend to use Stokes. So this is discrete particle settling. We're assuming that the particles are not like coagulating and sticking together, and they don't interfere with each other as they settle. There's a bunch of discrete particles. We typically assume they're spherical and they're settling. And so they quickly reach terminal velocity. And we remember from fluid mechanics, particle settling in solution, there's several forces on the particle. Okay, so what are those forces that are acting on the particle? Well, first one is weight, right? W equals mg. Second one, acting in the opposite direction, acting up, is buoyancy. Right? Buoyant force is the density of the fluid times the submerged volume of the particle times g. And then the last one is drag force. Right? As soon as the particle has any kind of velocity, we have a drag force opposing that movement. And so we can combine all of those, and Stokes' law basically combines all of those and solves for the v that's in the drag equation. What is the settling velocity? Makes a couple other assumptions about that have to do with laminar flow, and you can get an equation like this that says the settling velocity is equal to g times the difference in the density between the particle and the fluid times the diameter of the particle squared over 18 times the viscosity. So what that means is basically the larger the particle, the faster it's going to settle. And that's coming mainly from its weight. That's going to be contributing to faster settling. And so we reach terminal velocity very quickly, and that is our settling velocity for the rest of the settling that's happening. So to think about how this applies to primary treatment and what particles settle out versus which ones don't, which ones are too small to, we can look at this diagram over here, which shows a rectangular clarifier where wastewater is coming in here at the top, or I should say it's coming in from the side and then exiting out this side. And so we have example particle 1, which is coming in at the top here, the flow, and then it has some settling velocity v sub s1. So it's small enough that its settling velocity is low enough that it gets to this other side. It has not settled to the bottom of the clarifier, and thus it's going to exit. Okay? So we can say for particle 1 that it doesn't get removed. Its settling velocity is too low. Now we can look at particle 2 right here that comes in at the same spot, and it has just enough time as it goes through the clarifier. Its settling velocity is such that it just reaches the bottom of the tank before we get to this side, right? So for and we're going to assume that anything that hits the bottom of the tank is removed. Okay, so for particle 2, it's barely removed. Now particle 3 has the same settling velocity as particle 1, but it's entering the tank at half the height. And so you can see that even though its settling velocity is the same as particle 1, since it's lower, it's just getting barely removed before it exits as well. Okay. And so what we can see is that depending on where it enters, it makes a difference, and depending on what the settling velocity makes a difference. But what we can say is that if your settling velocity is v sub c, and you enter at the top, which is the worst place to enter, you're going to get removed. If your settling velocity is v sub c and you enter anywhere else, you're also going to get removed, right? You can imagine this slope, but anywhere here, you're going to hit the bottom before you get out. So you're going to get removed. And if your velocity is higher than v sub c, same is true. You could enter here or anywhere, and you're going to hit the bottom before you get removed. So v sub c is what we call the critical settling velocity, that says any velocity higher there or higher is going to get removed. And again, because that velocity is dependent on the diameter of the particle, we can say we're going to remove all of the particles larger than a certain diameter. But if we're smaller than that diameter, it's going to depend on where it enters, and we're only going to remove a portion of those smaller particles. Okay. So how do we calculate the critical particle settling velocity? V sub c equals h sub 0 over theta. So what does that mean? Well, let's look back up at this rectangular clarifier. We have h sub 0 is the actual height of the whole thing, and theta is detention time, right? Remember we just said detention time is v over q. It's the average time that a particle would spend, or flow, or a peak particle particle or a parcel of water would spend in this clarifier. And so particle enters, it has to traverse this distance h sub 0 over a time that it's in the clarifier, which is theta. Okay, so it's a distance h sub 0 over a time theta. Distance over time is velocity. So v sub c is this height divided by the detention time, the time that the particle's in there. Okay. So this is going to get a little hard to type this equation in, but bear with me. You can write it in a better format than me. V sub c is equal to, here's this h0 over theta. So I'm just retyping this in the format that I can using this lecture delivery method. So that is equal to h sub 0 times, earlier I said, so theta is v over q, so if I divide by theta, I'm going to multiply by q and divide by v. So I'm just replacing v over theta with v over q. So h sub 0 times q over v, which is equal to h sub 0 times q over, and then v is the volume. In this case, my volume is my cross-sectional area A times h sub 0, so h sub 0A. And you can see then that these h sub zeros are going to cancel out, and I'm just going to be left with q over A. So if we think about that, the critical settling velocity, we start with that. That is equal to the flow rate divided by the cross-sectional area. Definitely not an intuitive result, but it turns out to be true. And we give this parameter a name, this q over A. We call it the overflow rate, or OR. So the overflow rate is actually equal to the settling velocity, but instead of using units of distance per time like you would with a velocity, we use units of, for example, like cubic feet per second per square foot, or million gallons per day per square foot. The units turn out to be the same as a velocity, but we just report them differently. So sometimes this is also called surface loading. And remember, it's not a function of tank depth, it's only a function of the flow rate and the area. So it doesn't matter how deep your tank is, i.e. h sub 0, that comes out if you just use q over A. Okay? So given what we know now, how do we actually analyze and design clarifiers? We're not going to spend much time analyzing clarifiers in this class, but we are going to do a little bit of clarifier design. And so I copied this table out of my PE review manual, the big thick book that everyone buys to take the civil PE. It has a bunch of typical parameters for primary clarifier design. I believe your book has something similar. And what are our main design criteria for primary clarifiers? There's two things. One is, well, actually there's three things. The first is your overflow rate, or your surface loading. So we just defined what that is, q over A. It's the main design parameter. And if we look down at surface loading down here, it says 800 to 1200 gallons per day per foot squared is typical. You might see it in different units, but there's a range that turns out to be a good range for that parameter for domestic wastewater. So how do we design clarifiers? We start by saying let's pick an overflow rate in this range. We typically don't have any control over the flow rate, coming in. That's just determined by how many people are in our city or how big our population or service area is. So we have a flow rate Q, and we're going to pick an overflow rate in this range. And given that overflow rate is Q over A, that allows us to calculate what A has to be in order to get good treatment. Okay. The second design parameter that we're going to look at is detention time, right? We said detention time has to be usually at least 2 hours to get good settling. And so once we have an area, in order to get again, we don't have any control over Q, and detention time is V over Q. So we can define our volume to some extent, but we already have an area. And so to get the volume, once we've defined what our area has to be, we can adjust the depth of the clarifier to get enough volume. Now it turns out that if you look down here at the specs, where is the depth? Basin depth, 6 to 15 feet, 10 to 12 feet is typical. Again, so we can't just do whatever we want. We're not going to dig a 50-foot deep hole in the ground to do this or build a tank 50 feet high. It's going to be a reasonable height, and this is typical. This also talks about shape, rectangular or circular. Circular is more common in my experience. Rectangular tends to be older tanks. So again, our main design parameters: overflow rate, detention time, and then sometimes there's a last parameter here. Okay, so I'm going to add this here: detention time, 2 hours or more. And then there's also a third one, which is weir loading. So weir loading equals Q over L. So remember I said we have at the end of the primary clarifier, either if it's circular around the edge or if it's rectangular on the effluent side, we have a weir at the top where we allow water to go over the top and the solids get stuck on the wall and settle. So the weir loading is how much flow are you putting over that per the actual length of the weir. So if it's a circular clarifier and your weir goes around the whole outside, then the length of the weir is the circumference of the circular clarifier, and then you've got your flow rate. And this is designed so that we don't have this high increase in velocity right at the weir. I mean, there's other reasons why this is important too, but you can think of it as if you were trying to put a lot of water over a very limited weir space, the velocity could go way up right at that spot and pull some particles back up in the solution. But there's other reasons too that this is limited. So weir loading, typical parameters in this ballpark. So you might design your clarifier based on these two design parameters, and then check your weir loading to be in this range. And if it's not in this range, you might make your clarifier even larger. Okay. So in your project, you're going to be designing some primary clarifiers, and you should check to make sure that the specs, the depth, the cross-sectional area, the shape, and so forth are within typical ranges according to this table. And then there's a couple problems on your homework that ask you to analyze these as well. There's an example problem in your book. If you want to use that in order to get some guidance on how to solve those problems. And so that covers it for primary treatment. Oh, last thing I want to say is not every wastewater treatment plant has primary treatment. As when we get to secondary treatment, we'll talk about the different types of secondary treatment, activated sludge versus trickling filters. Trickling filters used to be what most plants were designed around, and most of those require some sort of primary treatment in order to keep the trickling filters from getting clogged with particles. So older plants tended to have primary treatment and trickling filters. Now that we typically use activated sludge, which is suspended growth, we don't have these filters that can get clogged, and there's some settling that happens as part of the secondary treatment process. A lot of treatment facilities were built without primary treatment over the last 20 or 30 years. They were just, the wastewater comes in through preliminary treatment and goes straight into the secondary treatment facility, the biological processes. And so you don't see primary treatment as often nowadays, but a lot of plants are actually finding nowadays that if they were to make one upgrade to increase their treatment effectiveness, it would be to add primary treatment. And so some plants are adding back primary treatment facilities in order to increase their treatment, their removals and their treatment effectiveness, to decrease maintenance in their secondary treatment processes and so forth. So not every plant has this, but a lot do. And it does remove a lot of stuff. So it kind of just depends on your design. You don't need it, but it is a nice thing to have. I think most operators would agree that it's a nice thing to have in the treatment facility. So that's all for primary treatment.